Hello, and welcome to today's lesson on how moving coil microphones work. We'll begin today's lesson by outlining the fundamental principles behind moving coil microphones. Next, we'll walk through the components of moving coil microphones. Finally, we'll break down the individual steps between producing a noise into a microphone and hearing it amplified. So far, we have explored how the generator effect is employed in alternators to generate DC current. Building on this understanding of the generator effect, we can now delve into how a moving coil microphone operates. This lesson will enhance our comprehension of converting mechanical vibrations into electrical signals, furthering our grasp of the applications of magnetism and electromagnetism in everyday devices. Let's get started. Microphones are fascinating devices that convert sound waves into electrical signals. The heart of this process lies in converting mechanical energy, sound vibrations, into electrical energy. To do this, these devices make essential use of the generator effect, which describes how a potential difference, also known as voltage, is induced in a conductor when it moves through a magnetic field. This is the same principle we learned in generating electric currents using alternators and dynamos. To understand microphones, let's get a better understanding of their components. A moving coil microphone consists of three primary components: a diaphragm, a coil of wire, and a magnetic field. The diaphragm is a thin, flexible membrane that moves in response to sound waves. Attached to the diaphragm is the coil of wire, positioned within a magnetic field created by a permanent magnet. Microphones operate by converting sound waves, which are variations in air pressure, into electrical signals. When sound waves reach the microphone, they strike the diaphragm, a thin membrane that responds to these pressure changes. The impact of the sound waves causes the diaphragm to vibrate, with the extent and frequency of its vibrations corresponding to the characteristics of the incoming sound. As the diaphragm vibrates, it moves an attached coil back and forth within a magnetic field. This movement is crucial because, according to the principles of electromagnetic induction, as the coil cuts through the magnetic field lines, a potential difference is induced across it. This phenomenon is known as the generator effect. The oscillation of the diaphragm means that the coil also moves in both directions, resulting in the generation of an alternating current, AC. Each time the diaphragm vibrates, the direction of the current changes, producing an AC signal. The size and direction of the induced current vary with the diaphragm's movement, which means the electrical signal created mirrors the fluctuations in pressure of the original sound waves. This relationship is significant because it ensures that the frequency of the electrical signal, indicating how often the sound wave cycles, and its intensity, reflecting how strong the sound wave is, correspond to the original sound. As a result, the electrical signal retains the characteristics of the sound, effectively capturing its nuances. Once the electrical signal is generated, it can be amplified to increase its strength, making it suitable for further processing. This amplified signal can be recorded for later playback or analysis. Ultimately, whether through amplification or recording, this signal represents the original sound wave, enabling us to listen to, manipulate, or broadcast it, thereby facilitating communication and artistic expression. In today's lesson, we delved into the working principle of moving coil microphones and how they use the generator effect to convert sound waves into electrical signals. We learned that sound waves are pressure variations that cause a diaphragm in the microphone to vibrate. This diaphragm is attached to a coil of wire positioned within a magnetic field. As the diaphragm vibrates, it moves the coil back and forth within the magnetic field, inducing a potential difference and creating an alternating current in the coil. The induced electrical signal mirrors the original sound waves in terms of frequency and intensity, thus preserving their characteristics. This electrical signal can then be amplified or recorded for various uses, such as playback or broadcasting. By understanding these mechanisms, we see how moving coil microphones harness principles of magnetism and electromagnetism to transform mechanical vibrations into electrical signals, a fundamental process in many everyday audio devices. Watch the rest of the GCSE Physics course at Sophos Education.